In my last video, I took this circuit and we simulated it and we ran it. And these were the results we got in terms of AC readings. And we'll slide all those over. And the point I was trying to make was that the voltages, if you measured the voltage across each component, the R, say with a voltmeter, the L with a voltmeter, and the C with a voltmeter, you would get readings that would be much greater than the 10 volt source. But we have to remember in AC circuits there is a phase shift. And this analysis is showing me the voltage from each point. So if I go from this point to the left of the resistor down to my ground, I get my 10 volts. If I go from this point down to my ground, I get 9.2 volts. But notice that the angles are different. And I'll show you how that affects things. And then if I go between my inductor and my capacitor to ground, I get this last reading, about 1.9 volts with a minus 157 degrees. Okay? So if I measure that way with a voltmeter, I'll get those readings. But what will I get if I measure across just the resistor, just the capacitor, just the inductor? This analysis doesn't really allow me to see the difference, and we'll be able to see it visually when I do the trans analysis, but I want to go ahead and show you what the readings would be on a meter if you just went across those components. And of course you can build a circuit and you can test everything out. So what I've done is I've opened up a spreadsheet and I recorded the voltages and the angles for nodes 1, 2, and 3, and that came right off this SPICE analysis here. This is minus 2.54 times 10 to the minus 15th. Well, that is a 0 for all practical purposes. E to the minus 15 is a 0. So that is that angle. 9.1 angle 23. I rounded it 23. 1.9 angle minus 157. So I got the angles exactly off the analysis. Then I converted them to rectangular complex. So 10 angle 0 is 10 plus 0i. 9.2 angle 23 is 8.5 and 3.6i. So I'm just doing a conversion. Complex, polar complex to rectangular complex. Both first quadrant. Now I move to the last one, 1.9 minus 157. And that's actually third quadrant, so both of them are negative. And that's what the X and Y values, or the real and imaginary values, work out to be. Minus 1.7 and 0.7i. So this is one of the things I've done in class to try and get y'all comfortable converting. Now I can go in and I can look at the voltage drops across the resistor, which would be the node 1 voltage minus the node 2 voltage. So whatever the node 1 voltage is, I subtract the node 2 voltage and I get it. Well, if I come over here to this part where I've got the rectangular, it's easier to do the subtraction. And so what I did is I just subtracted. 10 minus 8.5 is 1.5. 0 minus 3.6 is minus 3.6. So that is my rectangular value for the voltage drop across R. And I did the same thing for the voltage drop across the inductor. It's 2 minus 3. So it's 8.5 minus a 1.7, which gets me to 10.2. And it's 3.6 minus a minus 0.7, which puts me at 4.3i. So those are the rectangular values for that voltage drop, or the voltage across the inductor. So I've got my R, I got my L, and my C I get directly because one side of that was already ground, so that was the easy part. So then I can take those and go back to my polar form. And again, that's just what I had to start with. It converts back nicely. The 1.5 minus 3.6 converts to 3.9 at an angle of minus 67. So that would be the voltage. Now if you measured it with a voltmeter, the voltmeter would read that magnitude. That's why I made it bold. I did the same thing with the voltage drop across the inductor, and if you read with a voltmeter the voltage across that inductor, you'd get 11.1 volts. So you get 3.9 across the R, 11.1 across the inductor, and 1.9 there across the capacitor. So that's what I did to show you what the voltage drops would be if you individually measured them. Voltage drop across the resistor, 3.9 volts. Voltage drop across the inductor, 11.1 volts. And the voltage drop across the capacitor is 1.9 volts, and we got that on the original analysis. And what you notice is I have a 10 volt source sourcing it. So my individual measurements, if you were to add them up, do not add up to 10. But if you add them up in the rectangular, you will see that they do come out to be exactly 10. So my voltage across my inductor (10 volts in), all those voltage drops, and if you add them up rectangularly, 1.5, 3 minus 3.6 plus 10.2 plus 4.3i, and minus 1.7 minus 0.7i, you get to 10, 0, which is the applied voltage. It's exactly the applied voltage in the circuit. So it's 10 plus 0. And I'm going to bolden that just so you can see that we do in fact add up to the voltages, or those voltages do in fact add up to the source. So Kirchhoff's voltage law, even in an AC circuit, seemingly doesn't work, but in reality it does. If you do it with a meter, it will look like it doesn't. But if you take into account the phase angles, it absolutely does add up. And that's important to know from an AC standpoint.